I realize this is the first time that I've come to a conference with my boss. So this is kind of interesting here. I'm a little nervous, actually. So this talk, Are We There Yet? I think it was 18 years ago was the first BoostCon. Dave invited me to come and give a keynote. So it was a midweek keynote at the very first BoostCon. And I gave a talk that I had given a few times before and gave a few times after, called A Possible Future of Software Development. And this talk resonated well. I'm going to switch to my title slide here, if my clicker will do it. Or not. It was like just working.
Is the clicker on?
My clicker is on.
Does the space bar work?
The space bar will. No.
Okay.
What if you use the mouse to click on the arrow in the lower left corner?
Yeah, it's okay. Wow, it's like really interesting. So this is my title slide. So Bjarne Strustrup first asked me to give the first version of this talk at Texas A&M when he was teaching there, and so it was a little bit tailored for students at the time, and it resonated pretty well. I gave it as a talk for Texas A&M's industrial affiliate program or industry affiliate program, and so there were lots of people from industry as well as students who attended the talk. And after the talk, I got invited to repeat the talk for IBM research, for the F-35 Joint Strike Fighter team at Lockheed Martin. I gave it here. I gave it as a Google Tech Talk, and that Tech Talk's recorded. That was in 2007. And I heard from a number of people that it influenced their work, including from the designer of the Elm language, the Prezi presentation package, if you've ever heard of or used that. An individual named Ralph Thomas actually worked on some of the libraries that I'll show here with me for a while. And he went on to incorporate some of the work into WebOS, which was originally Palm and then HP, and I think now it's on LG TVs. And he also moved on to Tesla, and so some of the thoughts here are in the Tesla UI. Out of the talk, 2 years later, Software Technology Lab 1.0 was nuked at Adobe. I landed at Google for a brief amount of time, in part because of this talk and me giving a Google Tech Talk. I worked on Chrome OS. I'd love to say these ideas got incorporated into Chrome OS. They do not. Along another story. Have a beer with me sometime. So that's kind of the background. So I thought it would be interesting, partially a suggestion of Dave, who now, in part because of the first version of this talk, I have the opportunity to collaborate with Dave on this work. Software Technology Lab 2.0, we're picking up some of this work.
It's this one, not that one.
What's that?
This Dave.
Which this Dave Abrahams. So Dave Abrahams had invited me to give the talk here, and now we have the opportunity to be working together as part of Software Technology Lab 2.0, and we're picking up some of this work. We have a project internally called Project Code Less that we're working on. So let's get started with the talk here. The talk starts with looking at some industry developments. Since this was originally directed at students, I gave some stats on Adobe to give some background of where I'm from and some of our products. So I'm not going to go through the whole section of that, but I thought it was kind of interesting how things have scaled. So in 2006, there were 6,000 employees at Adobe. There's now about 30,000 employees at Adobe. We were doing about 2.6 billion in revenue. Now we're doing about 22 billion in revenue. I've spent a good amount of my career at Adobe working on or around Photoshop. In fact, the software technology lab right now is Photoshop adjacent. In 2006, there were 20 engineers on Photoshop. Now there are 250. There were about 30 quality engineers, with more than there were software development engineers in 2006. Now there's only 60, so that hasn't scaled up as much. And we can talk some about reasons for that. At the time, for platforms, we supported Mac OS and Windows. Now we have Mac OS, Windows, Linux server-side, iOS, iPad OS. You can run Photoshop in the browser, built in WASM. And we've got other platforms in the pipe. So that's for the ... there. So things have scaled up quite a bit. We rely a lot on shared technology groups within the company that develop a lot of some of the core technologies like type and things of that nature, which are shared across all of our products. In fact, Photoshop itself is built as a library, and that library is included in many of our other products. And the same is true of those products, which is somewhat interesting. I really didn't have a way to compare shared technology groups between the two. So I just put checkboxes. Yes, we do it. How we do it now is completely different than how we did it in 2006. So there was no way to do comparisons. In 2006, our process was very waterfall. On 18 to 24 month release cycles. We were still delivering boxes of software with CDs in them. And that put a lot of pressure on the development. Photoshop at that time the manual would count as a best-selling book, which means that to print the manual, you had to book time on the press, and those book runs would start almost 6 months before the product went out the door. For the manual to be accurate, that means you had to have some idea of what the features were, which pushes the process to get the features roughed in early so that you can do the screenshots, so that you can produce the books, screw the quality, you'll fix the bugs on the back end of the process, and now you're in a waterfall model. Our process now is much more agile-ish. We release on all of these platforms at regular cadence, and it's different on the products. The web version of the product goes out like every 2 weeks. I think the desktop is quarterly. iOS is like every other month. So there's this interesting cadence between all the products. So back in 2006, what were analysts saying about the future of software development? I pulled a couple quotes here. Gartner was focused on security, which I thought was interesting back in 2006, because that's a hot topic today with memory safety and security and how we do that. And we didn't fix the problems. And sometimes I think people think security is a new problem. Well, at one point, Adobe acquired Macromedia and had a product called Flash. And if you know anything about Flash, you know security is not a new problem. At Adobe. So they thought that there would be a huge shift towards security best practices. I think that has happened more on the server side than on the desktop and mobile side. It has certainly had an ongoing impact on desktop and mobile. But I don't think things shifted quite as far as the analysts thought that they would. I had this quote in just because I found this amazing, which was back in 2006, Microsoft was in the process of overhauling their complete software development process. And there was this comment at the bottom that says, yeah, it's not necessarily going to help them ship products on time or with fewer bugs. It's like, okay. But it gives you some indication that, shipping products on time and with fewer bugs was an issue, right? And still is an issue. So back in 2006, I had this conjecture about why I think the status quo would fail for how we develop software. It just can't continue to scale. And it's this quote what comes out of John Bentley's Programming Pearls, which is all the way back in 1986. So long predates this talk, 20 years before. And in this article by John Bentley, this was in ACM, he said, I've assigned this problem, he's talking about a binary search problem, in courses at Bell Labs and IBM to professional programmers and gave them a couple hours to convert the description of into a programming language of their choice. High-level pseudocode was fine. 90% of the programmers found bugs in their programs, and I wasn't always convinced of the correctness of the code in which no bugs were found. Okay. This is writing binary search with professional developers in major companies. Experienced developers. They had a hard time. Now, Mark Hamburg read this article. Mark Hamburg was one of the original people to work on Photoshop and said, I want to hire the 10% who could do this. And so when I hired on to the Photoshop team, I was handed the binary search problem. Say, write it. I passed, but barely. My answer wasn't great. Now this is translated to C++, so you can read it. This was John Bentley's solution to the binary search problem, right? So he wrote this article about it. He's had all these people look at it. They've studied the problem. And this is John Bentley's solution. And if we walk through it here, well, first thing we realize is if we don't find it, we found a position of where you would insert it, we throw away that information and we return -1 to indicate that we didn't find it. So his solution throws away some information. It's okay. I mean, the specification was to determine whether or not it's there. But it's doing all the work to find where it would go and then throws that away. It's got a possible overflow right here. L plus U could overflow. It's got an additional and unnecessary comparison here. Okay. And it generates an index. It won't actually dereference it for the array that's out of bounds, but it generates a negative index potentially for the array. If our array is empty, it will generate a negative index on that -1 there. So my 2006 talk, I gave this. This would be a correct answer to the binary search problem. Okay, and this is pretty much straight out of STL. This is a beautiful piece of code. It won't overflow. It does first plus last minus first to avoid the overflow. Has no unnecessary comparisons in it. That's a beautiful piece of code. So my conjecture, and this is again from 2006, was if professional developers can't write binary search, how is it possible that we create these massive products? Right? Photoshop, Acrobat, Microsoft Word. How do those things exist? I'm going to leave that question hanging in the air for a little bit. We're going to come back to that. Okay. Now, I actually think at the time that I gave this talk, we were in what I refer to as the Java Dark Ages. And this is where Java was getting taught heavily in school, and it was Java, object-oriented programming, and design patterns. And the graduates were really bad at programming. They couldn't write an algorithm to save their lives. They didn't know how the machine worked fundamentally. It got to the point where trying to hire new grads, I would be the first interviewer on the team so that I could weed them out and just send them home and not waste the rest of the team's time. And I was sending candidates home, and my recruiter said, this is, you're embarrassing these people, right? This is bad. And can you give me something to weed people out? And I said, okay, here's my question. Ask all of your candidates to give you a binary representation of -1. And my recruiter said, well, what's the right answer? I said, I don't care. Right? If they can't give you an answer, I don't want to see them. Okay? I accepted an answer that was okay. So I think in part because of programs like Google Summer of Code and coding competitions, I saw this huge uptick in people who were actually able to write algorithms and write efficient code and do much better. And so I was going to come in here and say, I think we're doing better than 90% now. It's been a long time since I've hired a new grad, so I don't know for sure, but my gut feeling is we're doing better, a little better, okay? But I was talking to somebody who I mentor, who's relatively young and fresh out of school, and he said, I don't think we're doing better. He said, I think now it's LLMs and it's JavaScript, and I think we're back in a new dark age. So I don't know, but if that's true, I think it's unfortunate. So what are analysts saying now? Well, it's all about AI. Almost all developers will increase their use of generative and machine learning as code assistants and low-code, no-code tools proliferate. More than 55% of developers automatically generate 40% or more of their code in their IDEs, highlighting the widespread use of generative AI and machine learning. I went through a ton of analyst reports preparing this talk for the future of software development. I found like one mention of security. Everything else was AI. Okay.
Where did that figure come from?
Good question. Yeah, probably. They asked Copilot. That's the answer they got.
It's just one of those, like, is this the fact that gets repeated until everyone believes it to be true?
Probably so. IDC actually does a fair amount of job at researching these, so I'm sure it comes from industry polls. How good the polling is, I don't know. So, if it's all about AI, I gave the binary search problem to Copilot. I've actually done this about every 6 months since about Copilot 2.5 came out. It's gotten good. So this is the answer. It's almost token for token identical to my solution. There's no bugs here.
I wonder why.
Yeah, wonder why. The name is kind of weird. The name it basically pulled out of the a description of the problem. So binary search insert position, right? Because you're looking for the first position where you would insert an element. And so I asked it, could it make any improvements? And it said, yeah, the name's kind of weird. Maybe it's lower bound, which, since STL came out, an acceptable answer to the Photoshop binary search problem is call lower bound, right? You can read the description of the problem and realize it's lower bound. You don't have to write the code. So the AI passed. So I guess we're done, right? I mean, that's the end of my talk. So I hope you guys don't mind missing your job. We have a little more time, so if you want me to keep talking, I can keep talking a bit. Let's take a look a little bit more at the past. We were talking about how we build these big products. This is a bug graph from a release of a product. I've been told not to name products, so it's a release of a product. So this was in 2005 is where this bug graph actually came from. And the interesting line is the total open bugs. They're the red line going way up to 2,500 bugs. And then right here, it goes really steep, straight linear down. How does that happen?
Bug bankruptcy.
Will not fix.
Yeah. What happens? You got a target ship date. Okay. So management says you guys need to clear X number of bugs every week. Defer them, right? Whatever. Get them off the plate. So that's how that happens. So I tried to look at how do things look today. These graphs look much scarier than they are. I put them both together. This is in part because of my complete inept ability to get a decent graph out of Jira. We started using Jira apparently back in 2015. I ran the stats all the way back to 2015, not because I was interested in the complete thing, but because no matter where I started the graph, it always started at 0. And so everything was just wonked. So to make it an actual 0, I had to go all the way back to 2015. What we're looking at here on the top is the total accumulative number of created issues, which is why it's always going up, right? And the green line at the bottom is the number of issues that are actually getting resolved, okay? And the blue line down here is the cumulative gap between those. How many unresolved bugs do we still have in the database? The hockey stick right here, I mentioned we have 250 engineers now on the Photoshop team. That represents when I came along and said, hey, you know what? We could turn Photoshop into a complete ecosystem. It's no longer just a product on Mac and Windows, but we can do it server side, and we can do this whole complete ecosystem. And suddenly we had double-digit growth again, which means we had a huge investment. And so that represents the number of engineers just skyrocketing on the team. Okay, so you have more engineers doing more work, you get more bugs, but you also resolve more bugs. So you can see that kind of unstabilized things right here. We had a little bump in the total number of bugs, and then we've been trying to get a handle on it. Okay, but the good thing is that's flattening off. Okay, as our processes improve and we're able to deal with this more complexity. You start to see, initially we didn't track the version releases down there, but you can start to see as we start to track them, that's a lot of releases, 103 releases in that small gap down there at the end. Dave Abrahams had a question?
So you showed the graph where there's this steep drop off because release date's coming.
Yep.
And bugs get thrown out essentially. Does the blue line include those bugs that are getting thrown out, or are those like every release that's all cumulative that we're not seeing?
We'll come to that. So right now the blue line is the unresolved bugs. Okay. So, but what does resolved means? Well, let's drill down just a little bit more. Here we've got a graph. This is total cumulative all the way back to 2015. So we have got roughly 54% of the bugs actually get fixed. Percentage would be a little higher because you have the cannot reproduce and working as designed bugs. That's in the yellow and purple section up here. And so those are basically not a bug, right? That's how those get resolved. So then you've got about 9% of the bugs that are marked won't fix. Okay, it's not that they're not bugs, they are bugs, but they get marked won't fix either because they're considered trivial and too low priority to look at, or because they're in a component that's scheduled to be rewritten, okay, or is in the process of being rewritten. And so it's like, look, we're overhauling this whole piece. We're not fixing bugs in there. Or in some cases, a feature that's deprecated. If you have a bug in a deprecated feature, you let it go. Only 4% of the bugs are deferred. I thought that was a pretty good stat. But 9% are unresolved, okay? So, which means nobody's made a decision on them. Maybe we don't have enough QE people to take a look at them, or they did and they can't figure out what to do. So that's not a great stat. So we go back to that question. How do we ship software if we can't write a correct binary search? And the answer is iterative refinement, right? We write some code, we test the code, we find there's a bug, we fix the bug, we patch the bug, we repeat. We lather, rinse, repeat, right? So our methodologies are designed around iterative refinement. We don't solve the problems, we approximate solutions. I should say. So how would we come about to write better code? Well, first we need to study how to write correct software, how to go about doing that. We need to learn how to write algorithms once and in a general form that can be reused. We should focus on fundamental algorithms, the ones that get used the most, and then compose larger systems out of proven components. And that basically describes the ethos of generic programming. Right? In 2006, the idea of generic programming was actually still young. In 2002, Alex Stepanoff came to Adobe and gave a talk on STL. It was the first time I met Alex. Found out a few years ago that the video is actually online. If you watch the video carefully, I'm in the front right corner of the audience. After that talk, Alex and I talked for several hours, and he was a VP at Compaq that was getting acquired by IBM at the time. And after a couple hours, he said, I really wish that I could go back to engineering. And I said, why don't you? And long story, that's how STL 1.0 came about. Alex came and joined Adobe, and he and I worked together for about 8 years. So way back in 2002, Alex put up this slide, is STL successful? He said, well, there's millions of copies out there. Everybody, including Microsoft and IBM and Sun, companies you probably don't associate with STL these days, had shipped it. There were a dozen books on the topic. There were very few extensions. What Alex means by an extension to STL is something like BoostGraph library, right, which was shipped in 2000. So that was one of the extensions he's talking about. Alex always viewed STL as an example for how you write code, not necessarily as this complete library in and of itself. In 2002, there was no language progress. The concepts hadn't appeared. We think about templates as being associated with STL. It's called the standard template library. But templates are just a mechanism. They're a hack for implementing generic programming. And he viewed it as having no effect in 2002 on software engineering. Now, I think we're doing much better today. I think if we look at that, STL and generic programming has had a huge impact on the industry. But I think it's important that we kind of go back to the original definition of generic programming, of what Alex said. So I'm going to walk through this a little bit. So by generic programming, and this is from Dave Musser's and Alex Stepanoff's paper that defined generic programming in 1988. Okay. We mean the definition of algorithms and data structures. That's what we're talking about. At an abstract or generic level, accomplishing many related programming tasks simultaneously, the central notion, which gets missed a lot, is generic algorithms, which are parameterized procedural schemata. We're going to come back to that in a little bit, that are completely independent of the underlying data representation and are derived from concrete, efficient algorithms. Okay. Definition holds up well today. Some key points here. Programming with generics does not equal generic programming. Metaprogramming, does not equal generic programming. So what is generic programming? Well, generic programming is mathematics. Okay. So Alex wrote a great book, From Mathematics to Generic Programming, where he makes this argument. So what's the parallel here? In generic programming, we have semantic requirements, and that's the equivalent of mathematical axioms. Concepts are algebraic structures. What we refer to as a model, like a pointer is a model of a random access iterator, okay, is a model in mathematics. Algorithms are theorems. And what we refer to as a regular function is just a function in mathematics. Okay, function with no side effects. Same input, same output. In programming, we deal with complexity, okay, and efficiency. In mathematics, typically you do not. Now we also have the notion of a refined concept, which is a concept defined by adding requirements to an existing concept. In mathematics, you have this also. You can say, well, a monoid is a semigroup with an identity element, right? We added a requirement to a monoid. In programming, we say a bidirectional iterator is a forward iterator with constant complexity decrement. Okay. A refined algorithm, then, is an algorithm performing the same function as another, but with lower complexity or higher efficiency on a refined concept. Right? One of the fundamental ideas in generic programming was there was no room underneath it. If you had more information about your data types, then you could write a more efficient algorithm. And so you could never say, oh, I've got this bespoke implementation which is more efficient than my generic form. Because you could always figure out, well, why is that bespoke implementation more efficient? What properties does it rely on? And write the generic form of that bespoke implementation. So there shouldn't be any room underneath generic programming. Now, concepts. A concept is an algebraic data structure formed on connected requirements. This gets lost a lot. A quality is a unique equivalence relationship. Most people in this room have probably seen this and known this, right? So, we have equality as defined as reflexive, symmetric, transitive, but it's connected to copy, right? Copies are equal, copies are disjoint. The concept of a regular type is essential for equational and local reasoning, right? This idea that says we have this object, we can compare it for equality. If we make a copy of it, our copies are equal, but our copies are disjoint. So if we modify a copy, it doesn't modify the original. That's what we mean by disjoint. That allows us to say, I've got this value within my code, and I can reason about that value locally. Okay. Now, Alex envisioned, when he kind of came up with the STL, that there would appear like an international library of algorithms, okay, and data structures, corresponding data structures. Data structures exist so that algorithms can run efficiently. That's why algorithms are central. We could have this international collaborative library. I think maybe we could model such a thing after the International Repository of Mathematical Theorems, right? A collection of fundamental algorithms and data structures presented in a common form. Just like in the IRMT, we have all the fundamental theorems in a canonical form. And we could have a proven implementation in a variety of languages. Just like in the IRMT, we have our theorems are proven both through manually and through an automated process. And just like the IRMT, we should select our theorems for inclusion, our algorithms for inclusion, based on their abstractness, which is how large of a domain they cover. But in programming, we should add efficiency. Now, if you're in the audience and you're rapidly Googling, I haven't heard of this IRMT, it doesn't exist. AI made the logo for me. It's unfortunate. Building a cohesive foundation for anything is hard, right? We have 2,500 years of mathematics. Building a fundamental foundation for mathematics is hard. Building a fundamental foundation for programming is hard. We have examples going all the way back to 300 BCE in mathematics. We have Euclid Elements, and we have Isaac Newton's Principia, and we have Giuseppe Piano Axioms, if you're familiar with those, his Formularo Mathematico. And we have Bourbaki, who, referred to as Nicholas Bourbaki, but if you know the history of Bourbaki, it's actually a group of people, not an individual. There is no person named Nicholas Bourbaki. Elements of mathematics. Okay, so we have these great works to build up the foundation, and they come around every couple thousand years, right? A little more recently as we're coming up. We have some examples on the programming side too. We have The Art of Computer Programming by Don Knuth, started in 1968, and it's still going. I think Don is 88 now, so I don't know how much longer that will keep going. We have Communicating Sequential Processes, a very fundamental piece of work from Tony Hoare. I put Alex Stepanov's Elements of Programming up in this category as a very fundamental piece of work. And we have some libraries to go with it, right? We've got the standard template library, we've got the Boost Graph library, we've got the Ranges library, we've got some nice pieces of work. We've got a couple pieces of work in other languages too. And there's more books, right? I trimmed it down to just a few. But if you look, largely the major pieces of these are either the work of one person or a couple of people. It's very hard to take something and distill out, here's the fundamental requirements, and then you come along and you say, now I have to fit this next thing in. And it's a quadratic algorithm, right? You have to fit the next thing in and then redo your complete structure, right? The STL, even Alex's version of the STL, has flaws. But those flaws now are very difficult to fix because we've got millions of users of the STL, right? And so it's going to take somebody with a great vision at some point to come and say, I'm going to take all of the work in this space and I'm going to make it my life's work to consolidate that back into a whole. So this is a huge challenge. Now the language challenge. We've made significant progress in language support for concepts. We still don't have a way to express semantic constraints, right? Those are still comments. The best that we do is we say, well, if we require that it implements an equal operator, and we require that means equality in a comment, okay? But requiring that something implements equal isn't the same as specifying what the semantic requirements are of equal. So, and there's lots of trade-offs here with how we do things. Separate compilation makes refinement difficult, and it impacts both efficiency and expressibility. I've been doing a fair amount of programming in Rust these days, and that's something that I've been bumping into quite a bit, where I would get away with things in C++ because templates get instantiated later, and so I could play a little fast and loose and get the effect I want. When things are separately compiled and you have safety in there, it gets harder. And the concept mechanisms that we have are used for implements as opposed to model, right? What I mean by that is we have concepts like copy constructible. Okay? Copy constructible is not a concept. Okay? It doesn't have any meaning at all. Copy doesn't have any meaning at all without equality. Okay? The concept is regular. Okay? That's a fragment that says it implements one operation of regular. Okay. Similarly, in Rust, you have things like std op subtract. You can't define subtraction without defining addition. Okay? That's not a concept. You have a protocol hashable. Okay? Hashable is actually part of regular. That's from Swift. Okay? That's a fragment. That's this thing implements this operation, not models this concept. And there's still a huge amount of confusion over what I refer to and Alex referred to as the domain of operations. And what I mean by that is if we have a type like double and we want to sort doubles, and sort requires that the type that we're sorting is a model of a strict weak ordering. Double does not model a strict weak ordering. Okay? But the domain of the operation says if we pass only doubles that are not nans, then it satisfies strict weak ordering. And so in that sense, double satisfies strict weak ordering. And that's a very important point, is that concepts are defined relative to the domain of the operation. And this gets huge issues with the C++ standard library in that domain of the operation appeared all over the original STL documents and in early versions of the standard, and it's been almost entirely expunged. And that's a huge problem. So a type models a concept, if the values of that type exist that satisfy the constraint. Okay? So what does that mean? I could have a type that only had one value in it that satisfied my constraint. And I could still say that that type models my concept so long as I'm only dealing with that one value. Okay. So again, operator less than on double does model a strict weak order. Yep.
Do you have any comment on precondition expressions and how that affects the domain modeling problem?
Oh, exactly. I mean, this is all about domain of an operation is all about a stated precondition.
Right. But that's
right?
not
Right.
done, but it's slated for C++ 26, right? Does that not satisfy your concerns, or?
Depends on how that gets incorporated into the standard library and the terminology. It could help. So, current design of large systems. Almost every large system I look at becomes a network of objects, and these form incidental data structures. What do I mean by an incidental data structure? I mean, there's no place in the code where I can go and say, where is my graph of objects? Where is my structure of objects? Messaging between those objects form incidental algorithms, right? As soon as I start messaging between my objects, I'm doing something. There's some algorithm going on there. I don't have any place where I can say, here in my code is where the algorithm is. It's distributed across my code base. We try to follow some local rules to approximate correct algorithms and structures. And then we iteratively refine back again until our quality is good enough and we can ship our product. So here's my generic algorithm for how we would go about building a large system. Identify the components and how they connect and interrelate. This is hard. It's doable. We avoid incidental data structures by packaging related objects that are related other than a whole part relationship as parts of a whole. So if I have relationships between objects, I want those encapsulated into a class, into some object type that manages the relationships between the parts.
Wouldn't that type encapsulate your entire program?
At some point, it always does, right? You want to do it as narrow as possible so that you can actually reason about the code.
But you have to prove that you can.
You have to prove that you can. You have to prove that the relationships are upheld. You have to establish what the invariants are of that class that uphold those relationships. Which is what I say there. The whole maintains the invariance of any relationships between the parts. We want to avoid incidental algorithms by recasting them as explicit algorithms, right? Look at how, instead of being send the message to all of the objects, write the algorithm that says do this with this structure of objects. Identify the common structures in algorithms and then refactor those into generic components, right? We can't build this massive library of all of the reusable parts. We have the standard library, we have pieces of it, we have fragments of it, but we can do it every day as part of our business, right? We can say we will identify the pieces that we're going to use within, and we're going to create libraries within our organization. And maybe we're going to open source those, and they are going to become libraries within our industry. And maybe eventually those will become standardized, and then eventually somebody great will come along and make sense of the whole picture. That's our goal. And then we repeat. So question, is generic programming, as I've described it here, sufficient to build software at scale? Right? If we really want to build very large systems, does this work? What do people think?
Yes.
No.
Yeah? Yeah?
At some scales, yes. At larger scales, no.
Yeah. I mean, Dave Abrahams told me at one point, oh, did I skip a slide there? Bigger is different. In 2006, I put up this conjecture. I think it holds pretty well, which is all problems at scale become a network problem. What do I mean by network problem? Well, it's that we have a set of related components, and we need to somehow establish local rules that if they're enforced on the local rules, then the properties of our system as a whole are upheld. Okay? And the system scales to the point where we can no longer reason about all of the individual pieces collected. So we have to come up with a set of rules that say, so long as I uphold these rules everywhere, then the properties of my system as a whole are upheld. Okay. So bigger gets different. And that brings me to this notion of declarative forms. This is my term that I use. What do I mean by declarative forms? Well, it actually goes back to something that John Backus referred to as functional forms in this paper on functional style programming. This is his Turing Award lecture. At the time, John Backus identified just 5 functional forms. And they were composition, construction, conditioning, which is like, if, then, iteration, and recursion as 5 functional forms. And Alex read this paper, and Alex said, these are theorems, very, very basic primitive theorems. And there aren't 5, there's infinitely many theorems if we map this onto mathematics. Okay, so similarly, declarative forms are theories. And there aren't 5 declarative forms, there's infinitely many. But I think there's a small number of foundational forms, some of which we know, and some of which are yet to be discovered. So what do I mean? Well, a declarative form is something that describes the components by their structures and constraints, typically in a domain-specific language, which I refer to as a combination of 4th generation and 5th generation languages. For anybody who's too young to know the definition of 4th generation and 5th generation languages, a 4th generation language is basically a domain-specific language. A 5th generation language is one that's constraint or logic-based, where you describe the solution in terms of the specification of the problem. The canonical 5th generation language is Prolog, right, as a logic-based language. And what I mean by 4th generation, 5th generation languages is I want domain-specific languages that describe the solution in terms of the specification of the problem. Right? So the DSLs should not strive to be general purpose or Turing complete. That doesn't mean that they can't be Turing complete. Avoiding Turing completeness, or even effective Turing completeness, is incredibly hard, right? We discover Turing completeness everywhere. So it's not a goal to make these things Turing complete, but it's also don't make it a goal to avoid them. So some examples, existing examples. Lex and Yak and BNF-based parsers are an example that falls in this declarative form space, right? Parsing in general. We describe parsing in terms of a grammar, and then we build a parser out of it, not in terms of some imperative code that says, if you see the next token, then do this. Then if you see that token, then do this. SQL, there used to be a whole number of relational database languages. SQL kind of one, definitely falls in this category. HTML, if we ignore script tags, falls in this category. It's a declarative way to specify a layout without saying this button goes here and then put that button over there. Type systems themselves and schema-based languages, right? Protobufs fall in this category. Spreadsheets fall in this category. Right? So a generic algorithm for building large systems is first apply the algorithm that we just gave for building systems in general, then identify the common rules governing related components and the structures that they form. Choose a DSL that allows you to define the components by expressing the structure and the constraints. If a DSL doesn't exist, develop one. And repeat. The asterisk there is because developing a DSL is currently hard. Okay. This fundamental point about does this work is that yes, it does. Rules exist. Rules are there to be discovered. Okay. When we're developing, too often we think we're inventing. I give a talk, forget what the actual title of the talk is, Goals for Better Code or something like that was one of the titles of the talk. But in there I have no raw loops, and that's where that's a rotate phrase comes from. C++ seasoning. Thank you. So I give that talk. And part of that talk is to say, look, if you're writing a piece of code and you find yourself writing a loop, think about what is that algorithm and see if you can identify the algorithm within the standard library. And if you can't identify it within the standard library, can you identify it in another library? Okay, and pull that in. If you can't do that, can you find it in a book or a paper? And if you can't do that, you are really fortunate. Okay? If this is a useful thing, you are really fortunate. Like, write the code, write the paper, get it named after you, get a promotion. Okay? This is great. This is how the process should work. Rules exist. The fundamental algorithms are there. They exist. The rules that govern our systems exist. They are not ad hoc. We don't have to iteratively refine. We need to iteratively discover what those rules are and figure out how to package those so that we create something that we can build upon. So way back in 2006, I had this library, which is known as Atom, and it's creates something called property models. And I showed this dialogue. This is a very simplified version of the image size dialog from Photoshop. It lets you specify a document in terms of width and height. The names up here are horrible. These should really be like original height and width because those don't change. Those are just showing you what the original height and width of the document are. You've got a checkbox to toggle whether or not you're constraining proportions. And you've got a percent checkbox so that you can specify width and height in percent. Okay? And that's percent of the original. So very simple. So I asked Mark Hamburg, who I mentioned before as one of the original creators of Photoshop. He's also the person who created Lightroom. He's a brilliant programmer. I said, Mark, write the code for this dialogue for me. Any language you want, any framework you want. I don't want the code for the visual aspects of the UI. I just want the code for the behavior. What happens when I change a value? How does that propagate through? Okay. And so he used Objective-C and AppKit and wrote this code, kind of state of the art in 2006. The highlighted pieces of the code are the parts of the code that actually enforce the constraints on this system. The rest of the code is basically plumbing for the event handlers, right? You got to change event come in, we need to get the value, we need to send it in to do the constraint handling. Even the constraints you can see aren't all gathered together, even though Mark tried, he got most of them. If we diagram this out, it looks like this ball of spaghetti. There is some effort in there to do script validation, right? If you have a UI for something, you can also should be able to drive it from a script. So you need to be able to validate the inputs on your script. And then you have just this width and height and percent and constrained proportions, which is just a bool, and then a bunch of event handlers. And some of the event handlers talk to each other. And you get this spaghetti piece of code to flow that out. Now, you might think that this is somewhat contrived. When I look at Adobe's applications as a whole, roughly a third of their code across all of the desktop, mobile, web products are this. They're dealing with UI events and setting properties. Okay, a third of the code. And it's more than 1/3 of the bugs because this is really hard to get right. Okay? The bugs tend to be really subtle. A lot of those bugs fall in the won't fix category. Okay? But nevertheless, it generates a lot of issues. So let's see if we can do a demo here. Let's see if I can jump out. And I need to mirror my display. Okay, somewhat visible. So I had to create a VM for this to resurrect code from 2006. So this is the demo that I gave almost 20 years ago. This was written in Mac OS in Carbon, which predates Cocoa, and Apple doesn't run Carbon apps anymore, hence the VM. It's also why down here this is more pixelated than up there, because Carbon never supported high resolution. But I managed to get this going. So this example right here is just a very simple dialog box where we can come in. We've got this slider that drives our numbers, and we can change our number, something like that, and it moves the slider. And this is our property model, a sheet borrowed from a spreadsheet. It's just got one value in it and its result. And then our UI description is over here. And it's got these bind statements that, like this binds against my value, which is just binding against my value in my sheet, which started as 42. And so the edit text field and the slider are both bound against 42. And so this is just a very simple data binding example of how things go together. But I can take the same thing and I can put in the mini image size dialog. Load that up. And here's the mini image size. I'm going to walk through this in a little bit more detail in a minute, but this is a functioning dialog here. We can type in values. We can say we want it in percent. We want to turn off constraint proportions and change one value and then change the other value, and then come back and say we're going to constrain proportions, and everything updates. Okay. What you're looking at here is pretty much the complete description. If I scroll up a little bit, got a comment at the top. That's the complete description that's driving the entire behavior of that dialog box. And what I've got going on here is I've got a declaration of three relationships, three constraints. And the way that these are described is each of these little relate blocks represents one constraint with two resolution functions to solve that constraint. Okay? And this one down here is conditional. So basically we're saying when we're constraining proportion, then width and percent is equal to width and height. And we say either because we're going to assign height to width or width to height, right, to satisfy that constraint. These are multiplicative relationships, but one of the values is pinned, making them a two-way relationship instead of a three-way relationship because they're dependent on the original value. So that's that. That's the model. And the UI just binds against that. And if we don't like that UI, our model doesn't change. We can just say open an additional UI. Okay, so this is another UI, an alternate UI on the same model. And we've got a little twirly down here with some sliders. And so we can drive the sliders. And if you look, these are both bound against the same model. So if I drive one dialog, it drives the other. And if I go back to this one and I drive it, it drives the first one. Okay? And we could keep going. We could have another description here. And here's another one where we put this down here, right? And now we've got three layouts, all interconnected. If we toggle the checkbox in one, it toggles in all of them. All of the behaviors are carried through. Okay. Now, I'm not going to go into extreme detail, but I will just show. This is actually the complete image size from Photoshop circa 2006. You won't find it in Photoshop today. It looks different. I want to pull up. The description here looks much the same. It's a little bit longer. You see we actually have some three-way relationships going on. The system supports end-to-end relationships. So these are always, these three-way relationships in this problem are always described as give me two values, I'll solve for the third, but the system supports give me any n values and solve for m values. Flowing through, and you can see many of those are conditional. And this is fully functional. And the one thing I wanted to point out here is this disable behavior, right? If I'm not resampling, then that implies I'm constraining proportions. And you'd see even if I uncheck constrain proportion and I said don't resample, constraining proportions would disable and turn on. There is nothing in this description that talks about when this value is this, disable that control, okay? What's the rule for enabling an input value within a UI? An input value within a UI becomes disabled if its value is implied by something else in the system and there's no contrapositive, there's no inverse, either because there's no inverse expressed or because the person who built the system choose not to express it, okay? But there's no way to go like, if I could click on constraint proportion to do the inverse to say enable or that would imply that my resample is checkbox. I could express that if I wanted to. You can get those both ways. This was an attempt to mimic current behavior, not to build best behavior. The other reason why an input value might be disabled in a system is because it's disconnected from your result. In this system, there's always a result someplace down here. This is in the output. There's this result down here. That's what's actually connected to the OK button, okay? And the OK button then is a latch. What this is the preconditions for my operation, okay? And so I'm going to come along and I can do these values. And if something becomes disconnected from the result, it's a don't care value. And so I disable the control. I have a question here.
Yeah. So this seems fine if your goal is to prevent invalid values from being entered or things going out of sync. But what if there's a case where you want people to actually be able to like have the invalid value and then like say, hey, there's an error here or whatnot? Like. Sure.
So we could actually show this because Photoshop has a limit here of a maximum size of your document. So, oops. I've got to be able to resample to violate 500%
should be invalid?
No, because it's adjusting my resolution because I was not allowing resampling.
You put X.
So now I can go really big. So Photoshop has a pixel limit on the size of a document. And so you saw my OK button canceled. Yeah. This is because when you've got a concave space as opposed to a convex space, sometimes it's useful to let the user navigate the space, but not continue. If I prevented them from typing in the large number, maybe they're going to change something else that would make that valid again, right? And so we let them go out of bounds, but we don't let them continue while they're out of bounds. Now the system, it's not shown in this demo, has all the knowledge about why you're out of bounds. So you could put up a message, or you could put a red dot next to the UI element that they want to change. However you wanted to express that in your UI, the knowledge and the capability is in the engine behind the hood. So we are going to jump out of here and go back to stop mirroring. Go back to play from current slide. Let's see. Now I've got a clicker. That's all it took. So for the mini image size, we kind of walked through already, but that's what the description looks like. Dave Abrahams and I have been looking at this going, we can do better. This is about, in a self-contained form, what we're hoping to get it down to. The property model library as it exists has no form of composition. I can't compose property models from other property models. That's something we would like to get in there. I think I know how to do that now after 20 years of thinking about the problem. And Dave had some great insights on that. But for this, I just expressed it flat. But really, what I want to be able to to say about this is we just have a single dependent unit conversion between percent and pixels, dependent because it's dependent on the original size, and then a single optional constraint. And so really this should be like 2 lines instead of 5 lines. Now if you compare that to the code we had before, right, this is nuts. Okay, this is more than 100-to-1 reduction in the amount of code. Okay.
Is there a missing closing parens on the first line then?
Is there a missing closing parens?
Yes.
Probably.
No.
Oh yeah. I see size. Yes, there is a missing closing parens. It's slideware. Okay. Thank you. I will try to get that in. Okay. So this is a huge reduction in the system. And if we actually graph out what these constraints look like, as opposed to the spaghetti mess, this is a graph of the actual constraints, right? We've got our 1 conditional constraint proportions down below. We have pixels and height. We've got the original width and height, which feed into those into 3-way relationships, and we've got a result popping out the top.
If you include the size of the engine in the code base, how many dialogues do you need to break even?
So I did that calculation in 2006, and the answer was we broke even at image size at 1.
All right.
Okay. So image size was chosen because it was a pathological case that had been originally written by Thomas Knoll, and then by Mark Hamburg, and then by Mark Poliger, and then I stubbed my toe on the thing. And nobody could get it right. There was always some subtle bug, no matter how we coded the entire thing. Within the whole image size that I showed there are 14 values within the system, and there is a path from every value to every other value. And the kind of bugs that you would hit would be really weird bugs. Controls disabling with the wrong state, or getting stuck in a disabled state at the wrong time, or you could click constraint proportions on and off, and your numbers would walk down and actually accelerate and eventually end up at 0. So all these little weird behavioral bugs, all fixed in this rendition.
Yeah. So maybe there's an analogy here with like regular expressions and like that being a DSL for certain kinds of things. But I find when I write them, the testing like dwarfs. Like I could cut half the code out, but the other half is all the tests, right? Do you have that same problem with this?
Yes. I'm not going to get into the details in it right now, but when we were deploying this 20 years ago, the number one question that I had in my office almost like every 2 weeks was an engineer would walk in and say, what I want to say is when I click here, disable that. And I would say that you don't say that. What you're telling me is you have 2 values. There's a relationship between the 2 values. What are the 2 values? What are their relationships? They're like, the relationships is when I click here, disable that. Okay. It's a different space to think in. It takes time to think in the space. Also in this library, we have within the little demo app that I showed you, we've got a little query language so you can query the model so you can see what's going on. And they give you stat crawls if you over-constrain a system. It gives you a stat crawl that says it's over-constrained. It always does that. It guarantees that once your system's running, there are no values that can over-constrain it. It's always structurally defined. So you always know up front. But still, if you get this spill that says, like, under these conditions, you're over-constrained, you're going like, that sucks. So one of the things in revisiting this that I want to do is build the graphs live and show you what's going on. I think that will help a lot. Question over here.
In this directed graph, you seem to try to denote stuff with empty arrows, solid arrows. Some of them are bidirectional, some of them are not. Can you explain a little bit about, a little bit more about the graph?
A little bit more about the graph, sure. So the values without the bars here are fixed values. So these values can be set by the user or can be calculated live. The little open-ended arrows, right? This hard arrow means that this is a fixed flow, right? Your original width while you're in here isn't changing. So this is a fixed flow. These double-ended soft arrows mean that they could flow either direction. Right, so you could also put in like no arrows. It's to be determined. The thing has to be flown out into a DAG. That's done based on a priority-based system. The little circle here means that this is a predicate, and the dotted line there means that that's a conditional relationship. And so that's going to be toggled on or off, whether or not I'm constraining proportions. So
And all of the circles are,
that's about it.
every circle.
Every circle is a relationship, and these things always form a bipartite graph. So there's never a box connected to a box or a circle connected to a circle. There's always a relationship between the boxes. Okay.
So going back to the display shoulder, I argue there's still a tiny behavioral issue that I saw. So basically, it had the checkbox for constraint ratio disabled. You type some numbers and then you clicked on it again. And then there was a number like 30 that got changed to 30.00, right?
It wasn't 30, but it was some other number, and it got filled in as 30.00, and that's because it's set to display 2. And so when I say constrained proportions, it has to pick which value to update to flow the graph. The way it works is the value the user most recently changed has a higher priority, so it tries to flow from there to the other one. It calculates the other one and displays it. It did look a little weird because we had one number without the .00, but the idea is that's where your cursor was. That's where you're typing, so you could keep typing there.
So if I understand, so this is a nice, simple data structure that you can describe, and then got an algorithm that does it, and that's how you can develop your UIs. You might point out something earlier, like there could be cases where the application, the larger document might supply, hey, you can't do that with like a button or like a red marker or something. You allowed for that.
Yeah.
But doesn't that just sort of break it where now you've created another incidental data structure by allowing that?
So no, it's not that from outside something pokes in and says, like, put up a red control. That's the UI that's just bound against this model, which is just reflecting the nature of the model. So I'm not poking values in. In fact, one of the problems with deploying this before is while this thing was updating, people would say, oh, you know what? I'm going to read this value and do some calculation outside the system and then feed a new value in over here. Why not? Because now you have an edge and a relationship that the system knows nothing about and can't guarantee anything. And I put an assert in that said, no, you do that, the code will assert. And I would have people in my office going, I'm going to remove this assert because it's firing all the time, but if I take it out, it works. And I'm like, no, it doesn't work. The assert's there for a reason. Oh boy. So yeah. And this is, like I said, this is one algorithm. This is one theorem. My answer is not that this is supposed to solve everything. This just solves a large class of the problem, of the problems, a significant subset. It's just like we bumped into this issue. Grammars won't let you parse a file that has a dictionary at the top of the file where the dictionary controls then where you find other things. A typical EBNF grammar has no comparable construct. An EBNF grammar can't describe every possible file format. Okay? So I am not saying that everything falls into this pattern. I'm just saying that a significant number of problems do.
How do you think about DSL versus library for this? Like, you had a DSL that defined these constraints.
Yeah.
Right. Presumably you have a parser, poops out your data structures. You could just say, like, here the public interface is the data structures. Give my engine the data structures wired together,
yes,
and I'll do it.
Yeah, it's got a full API, so you can drive it that way too. And in fact, it's built to interoperate with C++ very well. So and this is open source. It's on stlab.cc.
But the question is, how do you think about when to expose which to users?
Oh, yeah, no. My answer is you expose everything, and hopefully you have good documentation, and that people use it at the level that they're comfortable with. Ideally, I would like all of these DSLs to be embedded DSLs. But that gets really hard to get really tight expressibility in an embedded DSL in existing languages. So another area, if you're looking at language research, is how do you make a language really good at embedded DSLs?
So the old joke is, right, you have a problem that you can solve with regex, so you use regex, and now you have two problems, right?
Yeah.
So you have a slide here where it says, you have a problem, invent a DSL. Is there any concern? Everyone in this room spent a lot of time learning C++, right?
Yeah.
Is there any concern that if you solve every problem with a DSL, what you've created is like a Tower of Babel, where to reason about the full application. You have to understand the 15 or 20 sub DSLs it's using for its various problem spaces.
Yeah, so part of our project is I want the DSLs to be similar. Part of the project with the existing solutions that I put up there, HTML looks nothing like SQL, looks nothing at all like a grammar, okay? Nothing at all. And under the hood, they all have some common things. Within each of them, you can write expressions of some sort. Within a production in a grammar, you have an action that you want to take. That's a function. That's a functional form, probably is a pure function, is what you want. Within SQL, you have queries. Within HTML, you have styles and style expressions and things of that nature. And none of those syntaxes look anything like each other or follow the same rules. What you want to start to do is build a language within which you make it easier to build DSLs with common substrate, common infrastructure that can communicate with each other, where I can say from my grammar and my production, I can produce my schema. From my schema, I can attach my property models. And from that, I can attach my UI. And all of that UI or all of that syntax looks similar. Every place where I have an expression, it follows the same rules, the same grammar, the same order of precedence, all the things that typically trip you up, and build a cohesive system as a whole. So Zach, real quick.
Yes. So I think the charm, to answer that question, another answer would be the charm of a DSL in general is that I get to reason about my domain in a language that fits the domain and not reason about it, about solving the problem in the domain, and then also reasoning about C++. So there's very complicated mapping onto that domain. So if you're reasoning about 15 or 20 different subdomains, that's better than reasoning about 15 or 20 different subdomains and then 15 or 20 different ways that C++ maps into the subdomain.
Yeah. So Dave has a comment, but I'm going to have him hold that for just a moment. Only because I'm running short on time and I want to make sure I get through the last few slides. In 2006, I had this slide up, Future of Software Development. This is somewhat restated from how I had it in 2006 with better words. But basically, I said what we need to do is extend the ideas of generic programming to more domains. I think we're actually doing pretty good there. Like I said, there's a lot of confusion about what generic programming actually is, but the ethos is seeping in. We want to extend generic programming to apply to runtime polymorphism and get rid of this class inheritance and things like that. And then in languages like Rust and Go and Swift, you have protocols and traits and interfaces, not in the same order. Which lets you define it lets you define the protocol, basically the meta class of some sort, the concept, hopefully, and then you get runtime polymorphism for just saying you want a dynamic instance of one of those things. So I think we're doing better on that front. Hopefully we'll do better in C++ at the point when we have reflection and we make it somehow easier to give an interface to something, virtualize it. So I have a talk, Inheritance is the base class of evil, that walks through how to do this manually to create type erased objects in C++. That should just be automatic. And then I said we want to formally describe software behavior by expressing the structure and constraints of the system. So we're doing a little better on that, especially in the web space. I see much more declarative systems in the web space, but we've got a long way to go on that last bullet point. Wanted to throw up a few references. Back in the day, Jaakko Järvi and I collaborated on a bunch of this stuff. So if you're interested, there's a bunch of this is all just papers published on property models and a library down here called Hot Drink. It was a JavaScript version of the library. I think there's also a Rust version of Hot Drink out now. It's kind of fun to play with because it also shows it's not just for dialog boxes. It can do visual constraints. So in my domain, it's like how do you scale an image as you're cropping and rotating it? Those constraints are easily expressible, and then you can put a visual UI on top of it. In Hot Drink, there's demos where you like drag circles around and they push each other out of the way, described as a property model. Years ago, Jaakko Järve took a sabbatical. For people who don't know who Jaakko is, he was very involved in the C++ community, worked with Bjarne Strustrup at Texas A&M, was one of the professors there. He did lambdas in the Boost library, and then was very involved in lambdas as a language feature within C++. And now he's a professor at University of Turku? I'm going to mispronounce it. He's Finnish. It's in Finland. So he took a sabbatical and spent some time with me at Adobe. And we said, property models are about relationships between discrete properties. We want to talk about constraints on collections of things and describe them in a similar fashion. And the first thing we bumped into was that there was not a good way to talk about selected objects within a collection, just like what you would think about, I shift click from here to here and that selects the range. There is so much variance in the implementation. It's unbelievable. It's called out in this paper. And so many apps that don't get it right or don't implement it at all. It's all over the map. So we said, we really need to nail that. So we wrote this paper. If you're doing anything with UI, please go read that paper, because I'm so sick of horrible selection models and applications. And it defines a calculus for doing various forms of selection in any dimension. So you can do, if you've got a grid of pictures, it tells you how to select objects in your grid of pictures. If you have text and it's word wrapped, it tells you how to create selections in text. It tells you what if you want disjoint selections in your text, which some editors do now, how to do that. The whole no-raw loops, a good part of that came out of this thought process. And like, how do you manipulate a collection of things? And this is where the gather and slide algorithms from that talk came from. Now, Jaakko, this is without me, has actually gotten back as of 2023 to continuing the work on collections. And so he's published a number of papers. I didn't realize till I was putting together this talk, are we there yet? Is the title of one of his papers. So I thought that was pretty humorous that we picked the same thing. So he's also looking at how do we extend this onto collections. So what do I think about the future of software development now? Well, I think a lot of the same stuff holds. We need to continue to improve generic programming support in languages, including refinements and dependent concepts, and what's referred to as the law of exclusivity, which is surfaced. The term there comes from Swift community. But whole part relationships are essential for local reasoning. And we need to keep working on minimizing the trade-offs between efficiency and safety. We need to create better foundational libraries by implementing fundamental concepts and algorithms. We need to keep banging on that. I've kind of been shocked. As I mentioned, I've been doing more Rust programming. The standard library in Rust has a lot to be desired. So not everything is following in the footsteps of STL. I think we need to create libraries of embedded DSLs and ones that interoperate. We need to start solving that problem as a community. And we need to develop AI to reason about code so that eventually it can continue this process on it. AI is coming along incredibly fast. I'm probably one of those 55% of developers who 40% of my code is generated by AI, although none of it without modification. At this point, it's like having a junior programmer, and you have to do a lot of review and be super careful. But it's still, I find it incredibly useful and incredibly helpful. And I've given other talks where there's a language called Daphne, which will generate C++ code if you want to program in Daphne. Daphne is a language that lets you express code, including the constraints formally. So you can write your invariants, and you can write your preconditions, and you can write your post conditions, and then the the system will solve that those things are upheld for your code and give you an error message if they are not, or if it can't determine that they're not. The interesting thing is when it can't determine that they can't be upheld, AI, I have found, is incredibly good. Copilot is incredibly good at identifying what I need to say to convince the theorem solver that my code is correct, which is incredibly useful because then I've got a proven system. So I have some conjectures about that too, because AI, as far as Daphne code is seen, since once it compiles, it's correct. An AI has never seen incorrect Daphne code, right? So, so that's the end of my talk. I'm going to back up a little bit. Dave had a comment that I know he wanted to insert.
Yeah, well, I don't know if it's useful, but commenter over here, questioner, mentioned that you invented DSL to solve the problem, and I think that's one of the misconceptions that starts with generic programming and continues into declarative forms is that if you're doing it right, you're inventing things. It's actually a process of discovery, and you wouldn't come up with the system that Sean showed for describing user interfaces without a deep research into what's actually happening under the covers, right? And the main reason that you don't get into trouble so much with DSLs is you're actually discovering what's there. Now, my guess is that regular expressions were not invented with a view to the domain and the problems that needed to be solved there. For example, like the fact that they can be pathological in their performance, that's not something anybody would design into their system if they had a choice.
So on the regex thing, most of what I see is when people write a regex, they really wanted to write a parser. They really wanted a grammar. And so I view it as a misapplication in many cases. There are places where I think regex is very useful, but it's mostly misapplied where people run into problems with regex. And I think there's a danger here too, which is, with property models itself, I've seen it where people have a problem that doesn't fit this model, but maybe they don't see it up front, or maybe they're going to try to squeeze it in, right? They're like, well, it almost fits. If I put in this hack, I could make it work. Don't do that, right? You have to stand back and say, maybe I'm going to write that as a bespoke version until I understand what the heck it is, right? And maybe once you do understand it, maybe it will fit, maybe it won't. Maybe it will fit into something else.
So, a couple things. I have bad news for you about declarative languages like SQL. They all are Turing complete these days.
Of course they are.
Because, of course, just like the engineer in your office wanting to take out the assert, what people find out is that it's sometimes quite difficult to write the declarative solution, or they just can't figure it out, and they just want to write a loop. And unfortunately, then the standards bodies allow that to happen. Even HTML, if you look at XSLT, which of course is XML, but HTML these days is just XML in a different form. XSLT, for example, basically becomes Turing complete by adding if conditions and loops in a declarative form, which is a horror show to read and understand, because you basically have a declarative syntax that has now sort of become Turing complete in this weird way that is specified. So it's an unfortunate, I think, thing that maybe we should, I guess I would maybe argue it the other direction. If you think you're going to need Turing completeness, don't invent a new language. Don't invent a DSL, because you probably should just use a language that exists.
Well, that becomes part of that is the embedded DSL point, which is one of the things with property models. It's designed to work well inside of C++. So the types within this language are basically any types. They're not std any, but they're any regular as part of a library. The functions in there are just looked up by name. And so if you want to introduce a new type into the system, you can write a function in C++ that receives some set of arguments and returns a type as in any of your Photoshop document or whatever you want it to be. And now you've got a new type in the system, and now you can express relationships on that new type, and you can write new functions that take that type as an argument, and you go through it. It's all dynamically typed in the system. What I'm doing right now is working on the equivalent in the statically typed form. But that interoperability, because you always have the point where it's like, I want a function here, and so long as my function is pure, even if it's recursive, even if it's iterative, it becomes just a node in my relationship. And so long as I can prove out that this is a pure function, it's going to terminate given its arguments. I'm going to stay within the domain of the arguments and all of that stuff that we know that we can execute this function correctly. You can drop one of those functions into one of these systems. And that's why these systems get extended to allow that, because there are sound cases where that will work. Unfortunately, you open Pandora's box, and there's a whole bunch of unsound cases where you will think it works, and it does not. But a lot of people have spent a lot of time trying to build non-Turing complete systems. And then 10 years later, they discover it is Turing complete. Right. Because it's really hard. The fact is that you have any iteration or any recursion, even if you limit the recursion, even if you limit the iteration, it quickly becomes effectively Turing complete, right? If you say, oh, you can only recurse to a level of 10, and so I will stop you from being Turing complete because you can only recurse to a level of 10. Well, what am I going to do? I'm going to create a tree structure that's 10 wide, and now I've got 10 to the 10 iterations. And I'm not Turing complete, but I'm effectively Turing complete. It'll never terminate, right? So whatever constraint you put on the system, it's defeatable. It comes back to my, ultimately, like, safety is incredibly important, but it's also an illusion. Because if your system is Turing complete, I can write a C machine inside of my language, and then I can write all the same crappy code with all the same problems that I have in C inside of my safe language. Same thing happens with trying to build non-Turing complete systems. I think, Turing completeness is a force of nature. It is very hard to avoid.
Do you have any thoughts on applying this to distributed systems?
Yes. Yes. So at some point, I spent some time on property models, partially on the problem of how do you do editing offline and then reconnecting, and partially on the problem of what happens if you have high latency relationships, which happen if you're doing distributed systems or things like that. And it turns out there's some interesting work there, nothing formalized. This has been whiteboard sketches. But if you think about one of these property model systems, if I replace my values with effectively futures, and I flow my system with futures, as I can keep structurally changing my graph as input changes, even though I don't have actual values. And I immediately know when values become don't care, either because they became overwritten or implied by something else. And so those operations get canceled, and I can continue other operations. So there's some great applicability, I think, in there to distributed systems. The other thing about working offline is property models have a set of guarantees around them, which is if you once you determine the flow of a graph, the order of the operations for the contributing values and the order of the derived values is insignificant, except when it comes to moving to the next state in the graph. And it turns out that can be very important for doing like CRDT type of stuff where I'm trying to co-edit. I'm working on something and somebody else is working on something, or I'm working on something offline, and then I come back in and I'm doing my expense report offline, and then when I connect, the exchange rate changed, and the sheet can update without throwing away all of my work. Okay, and so there's some good applicability in that aspect of kind of distributed computation. Totally separate subject, but there's a relationship in my head between all of this and senders. But that would be a 2-hour talk.
As you grow a larger number of DSLs, how do you approach tooling for those DSLs?
Interesting. Not there yet, so I don't know. The system that I built here, underlying the UI layout system and the property model system, is a common substrate, which we refer to as CEL, which is Common Expression Language, and that's this thing that interoperates really well with C++, and it's kind of this common syntax and evaluator for a dynamically typed little language that interoperates well with C++. We're looking at doing the same. Yeah, wrap it up. I'm way over time, but that's fine because we're in Q&A.
You had a long-standing question over there.
Yeah.
Oh, one more question. So really quick. So I'm looking at redoing that in a type-safe way. Right now I'm working in Rust, which doesn't have great support for doing embedded DSLs other than macros, which get really messy. So I'm looking at how do I build that common substrate and build the interop between these. It's still an open area though.
Okay, so like that gentleman over there said, like learning DSLs is hard. As well as hard as writing them sometimes. And there's also like this hierarchy between like in research you'll see there's like one thing which is like formal verification method sort of thing, and then the other is like AI research.
Yeah.
And they sort of don't talk to each other as much as they maybe should. And then in between is like actual business logic, and there's sort of like this like schema of vulgarity between them. So DSLs tend to be like very DSLs tend to be more on the formal verification side. So how do you take that and move it through to the AI? Because AI need a lot of exemplars to learn something. So how do you get the AI to understand the DSL that you're running in the formal verification side?
I don't know. I'm not an AI researcher. I will say, surprisingly, as I've kind of resurrect some of this stuff, both, especially for the Eve language, which is the layout language. Eve stands for expression-based view engine. But that's the UI layout system. AI is surprisingly good, even though there's a very small amount of Eve descriptions out on the web at filling in the blanks and completing stuff for me. For property models, which is really weird because there's not a lot of examples of property models out on the web, it does surprisingly well. And one thing that I've noticed as I've been developing libraries as an interesting use for AI is that when AI gets it wrong, sometimes it's an indication that my interface is wrong because the AI is trying to follow patterns that it's viewed from looking at everything on the web. And so that means my code is breaking the pattern. And so sometimes it's like I need to do a better job at making my code fit the pattern, and then the AI will get it correct. So if I write things in a very normalized form, the AI will have a better job matching the patterns and understanding it. But yeah, as far as connecting the two, I mean, like talk to Wolfram Alpha or talk to Stephen Wolfram, who's been trying to do this with getting AIs to feedback on themselves. I know Cursor is getting better about when I write code in it, it will actually try to run the Rust analyzer on the code and then see if it has any errors, and if it does, it will iterate and try to get it correct. Unfortunately, most of the time when it falls into one of those loops, it's like, hey, look, if I take out all the code, it compiles. Here you go. So I don't have an answer. And we are over time. So if there's nothing else, you can talk to me